Yeah, thank you, everybody. We're Team FairPlay from the University of Illinois. And yeah, our project is kind of fair machine learning models using augmented electronics. Yeah, happy to be here. This is our team. I'm Brandon. I'm a PhD student at the University of Illinois. Then we have Shivam Benjamin, who are both master's students in computer science at the university. And then Venkat is a med student at College of Medicine. And they weren't able to join us today. But we want to give a thank you to our two advisors, Dr. Frost and Dr. Sun. Yeah, so I'll pass it over to Venkat and introduce our problem.
All right, thank you, Brandon. So we want to address the fact that with more machine learning models being used in medicine, that has the potential for a lot of strong studies being generated, but at the same time, that has the potential to amplify bias as a result of certain patient populations not being represented adequately in the data sets. So these articles here show a lot of different areas of medicine where underrepresented sample sizes of certain populations leads to bias produced by the algorithms. So if we look at the one on your bottom left, that's one highlighting the fact that when looking at kidney function tests for an African-American patient and a non-African-American patient, they'll have different values for their kidney function value or GFR, even if they have the same amount of creatinine in their system. And the reason for this is because of studies that were done starting around 1999, where they showed African Americans to have more creatinine in their system than non-African Americans, but those studies didn't have an adequate African American population, and they also haven't been backed by biological evidence. So these are the kinds of, I guess, clinical practices that happen as a result of bias in studies or algorithms. And moving to the next slide, we understand that a lot of times this bias doesn't occur as a result of the algorithms themselves, but as a result of underrepresentation, certain patient populations. So if we were to break down the United States by race, for example, we see that 67% of the population is white. That in itself will lead to disproportionate representation. And then when we look at the population percentage in clinical trials, these are the trials that guide best practices in medicine. It's even more disproportionate. So you can imagine that people in the Hispanic or Latino population, if they're only getting less than 1% representation in clinical studies, the results from that algorithm that are run may not be the most accurate for them. And then on the table on the right, we see, again, this is data that we took from a data set to put into our model. 78% of the patients in that set were white, and that led to a noticeable difference in accuracy in predicting readmission for these patients. So the way we want to approach this is by bridging that gap in representation between different patient populations. And Brandon will explain how we look to do that.
Yeah, thank you. So yeah, the first step is just to basically understand the scope of the problem. So before we do anything to try to solve it, we provide an audit of existing data to try to understand basically how disparate both the representation is, but also the model performance. We do this across different socioeconomic, demographic groups, also intersectionally. We compile it all into this kind of model and data set fairness report that we believe is immensely valuable regardless of anything we do downstream. But we don't stop there. So if you go to the next slide, we then kind of combat this problem head on. Using our FairPlay data generator, we're able to basically generate new patients of underrepresented groups to basically synthetically balance the data set to try to remove the underlying biases or incentives for unfairness. And so while we won't dive too deep into this generator on the next slide, we do want to stress that this isn't just like upsampling patients or augmenting or like some kind of smoke style simplistic generation model. This is a really large language model. It's basically ChatGPT for patients, where we're learning to simulate patients, specifically simulate patients of desired conditional types. In this case, demographic, socioeconomic conditional types. We've extensively validated this. On the top right here, we show that like data looks like just like real data. And on the bottom right, we have some results that show that like our data is basically provides the utility of real data. So we're really, simulating basically quote unquote new real patients. And using those new real patients, we're able to synthetically balance the data set. We can put it back into our flow. And then this data set no longer has all those, incentives for bias in those machine learning models. So we can return all those same problems that we want to use machine learning on within a healthcare setting, of which there are many, But now the models that come out of that construction will be fair. They can be integrated in any number of EHR systems through FAIR applications, and then deployed to hospital settings. And yeah, like I mentioned, so there are a lot of different tasks, and these range from clinical to business, like readmission predictions, severity prediction, which can improve patient care if we do better on them through this method. But also things that are like logistical or business, like claims act management or clinical trial planning, that can provide better resource allocation, better organization, things like that. So now I'll pass it off to Benjamin to talk about kind of our initial validation, our pilot study.
Yeah, so we conducted a pilot study on the task of patient readmission to the ICU. Concretely, this is the task of trying to predict whether a patient is going to be readmitted to the ICU after being admitted to a step-down unit. So we trained a neural network to perform this classification on the PhysioNet ICU data set. And the neural network is going to use diagnosis code, medication names, and treatment descriptions to make its decision. And then what we're going to do, or what we did, is we trained the same neural network on our enriched data set. This data set contains synthetic samples and compare those scores. So when you look at the EICU data set that was available, there's a public, the PhysioNet data set, it's a public repository of 164,000 patients across 204 hospitals in the United States. When you stratify the data set by ethnicity, you can see there's the largest proportion within the populations of the data set. And the effect here is that there's very likely to be bias in the downstream algorithms which are trained on these kinds of data sets. So, and to alleviate, to alleviate the bias within the underlying data set, we generate the synthetic data, which is supposed to fill in the gaps in that data set, effectively generating more synthetic patients from those underrepresented minority groups. And so the effect here, and then we evaluate the data set on unseen data, and so we can really just see side by side what the difference is. The experimental results indicate that essentially everyone improves across all the boards. You can see all patients column, but within those disparate categories, we also see improvement. But more importantly, we're able to see that the performance gap between all of the populations within the data set shrinks. And so the kind of big picture benefit here is that in the context of ICU readmission prediction, we're able to basically get closer to fair allocation of all kinds of resources. So within this work, we've also encountered several challenges and efforts on the ethical side. And so in regards to AI algorithmic bias within the healthcare setting, we try to bring forward an approach that's going to basically allow the sharing of data from multiple sources in order to effectively balance the data set from the perspective of these machine learning algorithms that then make decisions in people's lives. With regards to data and privacy concerns, our methodology requires de-identified data to be set up initially, but then can generate arbitrary synthetic patients of all kinds of populations or phenotypes, as Brandon mentioned. Yeah, and I'll pass it to Shivam now, who's going to bring us through it to the demo.
Sure. So what we're essentially trying to do here is create a solution which reduces bias right at the source, which is data, to give an objective understanding of its presence or absence and understand whether it's actionable or not. We have used industry standard technologies such as FHIR and the Smart on FHIR specification to make sure that no matter where you are, which EHR system your organization uses, you can deploy FairPlay into your systems. Let me show you how this would essentially look like. So I have a demo here. Suppose you are a clinician who wants to understand whether your current patient would undergo a readmission prediction or not. So you go to your list, which has your ICU patients, and you select a patient. This is a familiar screen for many clinicians where you see the snapshots for everything. But now what you can do here is you can go to the FairPlay Readmission Assist. And what this is essentially going to do is it's going to pull data in a secure FHIR format, which you could see here. And the FHIR format sort of gives you a JSON, which has a lot of features which you can evaluate. And finally, when you run the predict risk to patient, it's going to capture all that information and try to make sense out of it and give you a risk factor for readmission of patients. So this is something it would look like. So here you can see that the predicted risk of readmission is high, and the data that it used to sort of come up with that. Now, this is just one of the multitude of problems that can be solved if unbiased data is used in healthcare. We have already registered our app on the Epic App Orchard, and we are working on testing it so that we can get it production ready. We also plan to do the same for other EHR providers like Cerner or Meditech or wherever you are. For those of you here today, I would love if we can get in touch and you can try to deploy it on your systems and we can understand whether it works on your systems, because to understand how it's going to go. And you can just scan this QR code and get there, because we want to create an AI which leaves no one behind. And artificial intelligence based predictions are a gift. It helps in faster processing. It helps provide an objective failsafe, and it takes some load off overburdened clinicians. FairPlay ensures that AI leaves no one behind. Thank you.
I want to invite our judges to go ahead and ask questions of the team. Online judges, if you want to ask a question, just raise your hand and I'll shush the room.
So, there are over 500 different farms active in the US market. How does that factor into this? EMRs capture, depending on the ology, they capture data differently. So how did you think about that?
Yeah, there's two parts to that question, right? One is there's different EMR systems, right, to load this into. And obviously it takes work to make it out. But the idea behind using Fire, right, is that's more standard intermediary. And so, yeah, like you mentioned, right, we started with these, we're planning to move these, and obviously there's immeasurable amounts to go. The second part, right, is this idea that like EMRs capture different things. And so within these models, we're using ontologies, right? Like there's often a subset that is shared, like ICD codes, right? For diagnoses, procedures, often even if they don't use those or they use some proprietary, we can do some form mapping. So we're operating basically over those standard ontologies, but obviously there's mapping work to be done for certain groups. We need to map to those ontologies.
The framework is flexible in such a way that given whatever source data set we're kind of dealing with, the modality of the data, we're able to basically generate data within that same population, within the same style effectively.
Shalina, you had a question?
Yeah, a couple questions. So one, I really want to better understand the idea of like AI being objective, as well as the idea that machine learning will kind of remove all of the bias in data, right? So if you think about like genomic data, for example, when you predict genomic data, there are allele frequency differences in different populations. So you could look like you predicted it well, but you predicted it based on a certain population will not necessarily be of use for other populations that have different allele frequencies. So it sounded like that was a key part of the presentation. So would really like to understand, you know, how you all are thinking about that.
Yeah, exactly. You're dead on. That's like kind of this core idea that like machine learning models may not be biased themselves, but they're just kind of mirrors to the data set. And often the way they're trained, right, they want to do the best job on their whole training set. In a lot of cases, especially, right, where you call out genomic factors and things like that, where the biological differences are strong and clear, it's going to just learn the majority patterns because that's how it does best on its, you know, on the majority of its training data set. And so, yeah, that's exactly it, right? We take this advanced model that can learn patterns for different specific groups, as well as obviously kind of population-wide patterns. But then when we like generate new patients with these, you know, group-specific patterns, when we get to the downstream machine learning models, there's no longer going to be that incentive to learn the majority pattern because that's not how they're going to do best overall. They're going to need to learn the patterns for all the different groups, or some mix of them to do best overall because the trained data set is now more balanced.
So a couple things. One, I wonder if you have enough baseline data. Two, I'm assuming that a lot of EHR data may be missing or incomplete for a lot of different populations because, for example, some people may be on like Medicare, Medicaid. I think you might run into like insurance differences in data that may make some of your data incomplete. And three, if you haven't already, I would check out Ruha Benjamin and her work. She does a lot of work on AI and the impacts on people of color and how AI kind of repeats biases for people of color because of the lack of data. But overall, I think your idea is really interesting. I just lean in more into some of the baseline like assumptions that you're making about the generalizability and being able to get enough data on patients of color. And then how do you deal with some of the missing data and systemic things that are built into healthcare that will disproportionately bias different groups? But thank you for answering.
Yeah, thank you very much. And yeah, those are definitely challenges we're aware of.
So if I was just to add to that, you're right that right now the data we are using, we notice a significant improvement in results across the board for it. And the idea for FairPlay is for it to eventually get better. Since the data we are using is synthetic and de-identified, the more we deploy, the more we learn, the more we are going to get better. So the more people we partner with, it's only going to improve from there. And hopefully we'll be in a situation where we can objectively say that we're creating a significant difference in the bias that AI creates.
And also to address the concerns with actually the systemic issues that are the underlying source of this disproportionality in the data sets. The hope here is that with AI becoming a more mature technology that's more broadly deployed in all kinds of settings, the unvirtuous cycle of disproportionate data set, making disproportionately biased AI, causing then in turn disproportionate care to all kinds of populations in the data set. The hope is that we break that cycle by improving those AI models and debiasing them.
I think Lily, you have a question.
I'll go. I kind of have two questions. One, maybe I'll convert more to a comment and then we ask the subsequent question, because obviously the underlying data is a critical factor, and it's a well-known fact that women are underrepresented in clinical trials. And you didn't talk about that at all. It's not just about race. So as you look to create this model, you have to understand that some of the data out there is actually not representative of the whole population either. So there's many other factors that you may want to consider as you talk about your tool and how you want to address some of these biases. My question is going to go to, I have a couple, but the one I'm going to ask you guys about is, you want to present this data, at least with the example you talked about with the readmission. What's the behavioral change you're expecting clinicians to make based on the data you're providing to them?
Yeah, so thank you for the first point as well. Yeah, we're definitely aware that there's, any number, right? Gender, race, socioeconomic background. And the idea is like both the audit and the balancing can be done on any combination of those, and as well as intersectionally across them. Yeah, we presented one pilot, the stat that matched our pilot study, but yeah, we are aware that that is a main thing that needs to be addressed by the models as well. So thank you for bringing that up. And then on the second one, so many, I'd say most hospitals throughout the country have some readmission machine learning model at the back end. So Dr. Cross we've spoken with has mentioned basically, oftentimes they're relatively naive, but they point to patients that need more resources, right? If you say a patient is going to be readmitted with high probability, it's in the clinician's best interest to tempt them more heavily before they get readmitted, or make sure that they're ready to leave. And so the idea is these models are already guiding clinician behavior, but they're guiding them in a biased way. So the kid, what was the article you mentioned? The kidney function, right? Clinicians are making decisions already based on those models, but the models are biased. So they're making, not every single time, but they're more likely to make poor decisions for underrepresented groups. And so we're not necessarily trying to shift the reliance on these models or even say they should rely more, but we want the existing reliance to be more fair and unbiased.
And to add to kind of the decisions that are made based on the risk of readmission, some things that are done in the hospital are allocating specialized staff for certain patients, or deciding how often to schedule follow-up after discharge. So some of those decisions come down to what the algorithms say about how high risk they are.
So are there going to be any follow-up metrics that you implement within the tool?
Yeah, definitely. I mean, we have the first step, right? Is this auditing report? We would envision that report being done with your tool, right? To hopefully see, confirming
So you are out of time, but I just did want to give our online judge a chance to ask a quick question. Yes, go ahead.
Yep. Good idea, and I think this can have a great impact. So if you're looking at the problem of all races not being equally represented in the data, I'm not sure if accuracy is the only metric that you should be looking at, the model accuracy. There could be other measures that you can check to see what is the impact of your solution. But if you look at accuracy for now, you would expect that there will be a bigger jump in accuracy for the underrepresented races, whereas from the results looks like whether it's white or other races, it's almost an equal jump across the board. Did you notice that?
Yes, so we did see a similar side jump, like we said, like everyone tends to improve. I mean, the two biggest jumps are specifically like Hispanic, which is a very underrepresented group that performs the worst. So yeah, so you do call that out, right? And this idea is like, it's basically a sophisticated data augmentation approach. And also in the setting, like we're able to improve everyone, if that makes sense. We see it more pronounced in, say, a genomic setting, as the earlier question asked. So yeah, so like you mentioned, we do see similar jumps. The two biggest jumps are, in terms of quantity, are African American Hispanic groups, which jump past the previous overall performance. But yeah, you can follow it.
Okay, thank you.
Thank you.